Inductance, capacitance are LC circuit. We will be study about inductance, capacitance or LC circuit. What is the LC circuit? Okay, and its oscillations. Okay, differential equation of an electrical oscillator. Differential equation. Differential equation. Differential equation of an electrical oscillator. Okay, differential equation of an electrical oscillator. Okay, consider an electrical circuit in which an inductor or inductance L, inductance L, and negligible resistance is connected to a capacitor, Okay, this is the symbol of capacitor and this is the symbol of inductor. Okay, when the capacitor is first charged by battery, the electrostatic energy resides in the dielectric medium of the capacitor. As the capacitor begins to discharge through the inductor, a current begins to flow the inductor coils. Okay, this sets up a magnetic field around the coil. As the capacitor discharges, the electrostatic energy of the capacitor is consumed into magnetic energy of the inductor. There is thus a continuous exchange of energy between the inductor and the capacitor. As the resistance is negligible, there is no dissipation of energy or the form of heat. Okay, if L is the coefficient of self-inductance, if L is the coefficient of self-inductance of the coil and di upon dt, the rate of growth of current, then voltage across the inductor, voltage across the inductor equal to minus LDI upon dt. Okay, minus LDI upon dt. Okay, that is a minus LD square Q upon dt square, Q upon dt square. Okay, and voltage across the capacitor, capacitor is Q by C. As there is no source of EMF in the circuit, then LD square Q upon dt square plus Q by C equal to 0. Okay, as there is no source of EMF in the circuit. Okay, then d square Q upon dt square plus Q by LC, that is 0 R. D square Q upon dt square plus mu Q equal to 0, that is equation number 1. The equation is a differential equation of simple harmonic motion. This equation is the differential equation of simple harmonic motion of the electrical circuit. Okay. This equation is a differential equation of a simple harmonic motion for an electrical circuit. Okay, where mu equal to 1 by LC, or constant of the electrical circuit, or constant of the electrical circuit, or constant of the electrical circuit. Okay, from the equation number first, d square q upon dt square into alpha minus q. Hence, discharge of the condenser is oscillatory. Discharge of the condenser oscillatory. Its period is t equal to 2 pi under root of 1 upon mu equal to 2 pi under root LC. This is the equation number second. Okay, frequency is n equal to 1 by t, that is 1 upon 2 pi under root 1 upon LC. This is the equation number third. Okay, since the equation number first is differential equation of simple harmonic motion of an electrical circuit, its solution is q equal to q naught sin omega t plus phi. This is the equation number 4. Where q naught is the maximum value of the charge. Okay, q naught is the maximum value of the charge and known as the amplitude of the charge, and known as the amplitude of the charge. Okay, electrical oscillator in practice. Okay, then the inductance L always has some ohmic resistance. The inductance L always has some ohmic resistance, due to which there is a continuous loss of energy and amplitude of simple harmonic motion slowly dies down to zero if, however, corresponding amount of energy is supplied to the circuit from an external source. The amplitude of simple harmonic motion can be maintained. This is done by using a valve or transistor circuit. Okay, in this way simple harmonic electrical oscillations can be realized in practice. Example, frequency generator. Okay, thank you. Then in the LC circuit is and we will be studying about studying about vibration of a magnet. Okay, thank you.